Good morning, I am Owen Falzon, and in this presentation I will be talking about our work on hyperspectral data analysis for mold detection in cheeselets. This project involves a collaboration between the University of Malta and Farm Fresh Limited, a company from the Magro group of companies. In this work, we are investigating modalities and methods for the assessment of food safety and the food quality. Specifically, we are interested in methods that allow for the rapid, non-invasive and non-destructive detection of contaminants in food products, in our case, cheeselets. One appealing technology for this purpose is hyperspectral imaging, where we basically use a camera that gives us detailed information about the spectrum of a target of interest. For a brief overview of how a hyperspectral imager works, we can actually start by looking at how a standard camera works. So where we typically have the camera obviously pointed to the target of interest, and when light is reflected from the target of interest and reaches the sensor of the camera, that light is effectively split into three broad bands. One covering the blue part of the spectrum, one the green and one the red, and effectively this gives us three separate arrays, three separate images that are then combined to obtain one color image. The main difference when it comes to hyperspectral imagers is that instead of having three broad bands, we typically have hundreds of very narrow bands. So instead of just a broad RG and B band, in this case, we would have much narrower bands, a number of contiguous bands that cover the entire spectrum, but that allow us to kind of have finer detail at each wavelength for the target that we are looking at. So at the end of the day, we end up with an image where for each pixel we have a spectrum which is represented with a good resolution. One other advantage of these imaging systems that are available nowadays is that while until a few years ago the only systems that were available consisted of these kind of rather bulky setups where you had a conveyor or conveyor belt or a moving plate in order to slide the object of interest under a camera that obtained line scans. Nowadays we can find images that allow for rapid acquisition without any complicated setup, and that are obviously much more portable than these kind of more conventional setups. For the purposes of our experiments, we made use of a portable hyperspectral camera, the Specim IQ model that is shown over here, and this offers a spatial resolution of 512 by 512 pixels and covers the spectral range from 400 up to 1000 nanometers for a total of 204 contiguous spectral bands. The cheeselet samples we considered consisted of 10 samples that were inoculated with spores of penicillium and 2 samples that were used as controls. Eventually, we acquired hyperspectral data from these 12 cheeselet samples, so both the inoculated samples as well as the controls, over a number of days. And the idea here was to monitor the progression of the growth of mold on these samples. For reference, we also acquired corresponding standard RGB images. After the acquisition of hyperspectral data from the cheeselet sample, the next step involved extracting and processing data only from the region of interest from the acquired hypercube. So specifically here, we're just selecting a particular set of pixels that cover the surface of the cheeselet, and we just excluded the background pixels. After that, these pixels were used for further processing using principal component analysis. And the idea behind principal component analysis is to start with a set of correlated variables So what we mean by that in this case is that we're starting with pixels that share similar or common spectrum for different regions of the cheeselet, and eventually end up with a set of principal components that effectively represent uncorrelated variables. The resulting principal components are ordered based on the variance they explain in the original hyperspectral data. So we started with the original hyperspectral images and extracted the pixels of interest, applied PCA to these pixels. So effectively we applied PCA to the spectrum for each pixel location. After that we obtained the uncorrelated principal components and ordered these, and these were ordered based on the variance they explained in the original data. For the principal component analysis step, we took all the hyperspectral imaging data for a particular scan, and this exhibits a structure where we have X and Y being the spatial dimensions, and the lambda direction here represents the wavelength. So here we have this same representation in this cube format. In fact, the data is referred to as a hyperspectral data cube, where X and Y are effectively the spatial pixels, and if we look along this direction, we can see that we can extract the spectrum associated with each pixel. So effectively that's how we transformed our data. We extracted each pixel and the corresponding spectrum as effectively individual variables. So we started with an M by N by L data cube, and subsequently we transformed this into an M by N, or we're calling it here K, where K is equal to M by N, by L, because of the L frequency values, wavelength values associated with each pixel. This was our input data for PCA, from which we then obtained this transformation W to obtain the uncorrelated variables Z. So effectively we ended up with our scores and loadings Z and W that were obtained from the original data X, and from this scores we could reconstruct an image because these scores are of the same dimension as the input data, and we can reconstruct a set of principal components represented effectively by images of the data. This time, however, the resulting variables are uncorrelated, unlike the initial pixel values we started with. Here we are showing the first two principal components associated with a number of samples that were scanned. So what we are seeing here, first we have the original RGB images for the cheeselets. So we have a control sample and the 2 days for a contaminated sample. PCA was applied individually to each one of these, as well as obviously all the other samples on different days. And in this section over here, what we are seeing are the results for the first principal component, where we have the loadings, so the W matrix, and the scores, our Z matrix, effectively the principal components. And we can see that in the case of the first principal component, if we look at the control and the contaminated sample on day 1, we can observe these kind of gradual variations in intensity that are pretty consistent across all the pixels that are considered. These values also typically show a consistent polarity. For the contaminated sample on the second day, where we start visually seeing some evident changes in color, so here the mode was still in its white phase, while here it's in its blue phase. Then for the first component, we do see some changes even in the first principal component. What's of greater interest is actually the second principal component. And as we can see in the uncontaminated sample, in the control sample, there is nothing particularly interesting that seems to be associated with any contaminations in the second principal components. So the only thing we can observe is kind of these dimples that were also observed in the first principal component, and those are associated with the surface texture and some aspects of the illumination on the original, on the cheeselet. However, in the contaminated sample on the first day, where visually there wasn't much that could really be observed, here we could see that there was something going on in the second principal component. So the spectral characteristics of the white mold that was present in this contaminated sample but was not visually evident showed up very clearly in the second principal component. And interestingly, here we also observed that these values for the score images, we saw a change in polarity for the contaminated regions with respect to the uncontaminated regions. We could confirm that these regions are actually contaminated because over time we could see that there was this blue mold that showed up. One point I need to highlight over here is that there are some rotations here with respect to the RGB image. So these are the same samples. There should have been just some rotation for the purpose of alignment, but these were two different imaging modalities we're considering. In the case, yes, of the contaminated sample on the second day, kind of these differences showed up in the first component because at that point they were very evident, so they explain kind of a higher variance in the data, and so the second principal component then was a bit less of interest than the first one in this specific case. But this situation where we observe activity in the principal components that was not as evident from visual inspection, that's what's of particular interest to us in this case. So the previous procedure was applied to all the samples that were scanned, and what's interesting is that we observed very similar behavior for all the contaminated samples. In fact, over here we can see an overlay of the spectrum, so effectively of the loadings associated with the second principal component for all the contaminated samples, and we can see that we get a considerable overlay between the spectral representation associated with the second principal component for all our samples. Similarly, if we had to go through all the score images associated with the second component, would observe that there would be these patches that are representative of the contaminated regions on our sample. These were confirmed eventually because over time the contamination became visually evident because the white mold turned blue in color. So what characterized the first and second principal component was that in the first component there were typically gradual changes in intensity across the sample surface that was analyzed, and these were either associated with the texture of the cheeselet, so these dimples in this case, or the illumination changes due to the lighting system being used. And what's interesting that is, once again, the outcome for this background activity was quite consistent across our samples, but obviously that's not particularly interesting to us. What's more of interest are the results from the second principal component, where we saw that consistently across all the contaminated samples, the activity on the resulting images was characterized by regions of opposite polarity, and with the negative polarities in this case representing the presence of white mold. And as I already mentioned, the spectrum was very consistent across all these contaminated samples. So in conclusion, in this work, we wanted to evaluate whether hyperspectral imaging can be effectively used to detect the presence of contamination, in this case penicillium contamination, on cheeselet samples, And the reason for that is because if it is effective, hyperspectral imaging can provide a rapid and contactless and non-destructive approach to carry out such tests. We applied principal component analysis to the hyperspectral data and in fact showed that the imaging method with this analysis technique can in fact help us identify the presence of contaminated regions in the cheeselet, even at a very early stage when there are no kind of visually obvious clues that the food sample is contaminated. And our idea is now to also consider this approach for other dairy products and also potentially other food products to see if we can obtain similar results with different types of contaminants and different food products. Thank you.